morning, and welcome to the dating HPC dating game. So let me start, introduce the panel all the way down the end. Addison Snell, Chief Executive Officer of Intersect 360. Who's down? And then next to him is Henry Newman, Chief Executive Officer and CTO of Instrumental. And then next to him, next to him is Gary Greiter, Deputy Division Leader, HPC Division at Lannel. And then finally, Garth Gibson, Founder and Chief Technology Officer of Panasas. So we have actually a very esteemed panel here, and we have both technology and market to look at, and I think it's going to be an interesting morning. So with that, we can jump in with a couple of questions. And what I was going to do is give each panelist a chance to introduce themselves a little bit with answering the completely softball question is, what's the biggest hurdle to Exascale? Addison, why don't you start and we'll just work our way down.
Hi everyone, I'm Addison Snell with Intersect 360 Research. I'll start by giving the classic analyst answer of it depends. If you mean what the greatest hurdle to a peak exascale system is, the power and memory management are going to be ridiculous hurdles to try to overcome. The top 500 list, if you like using that for your market research, has not gotten remarkably more energy efficient over the last couple of years. And if you're going to make an exascale system, you got to figure out where all of these megawatts are going to come from. If, however, by exascale you mean from an actual usability standpoint, I'll change my answer and say software. Even today's, let alone petascale, terascale systems are not being efficiently used today. We ran a survey in May of this year asking people how many cores on average their applications used. Industry average right now, 36 cores. Being used for an HPC system. So I'm kind of waiting for efficient use of terascale, and those software issues will determine the path to efficient exascale.
Thanks. Henry.
And I agree with Addison on both accounts, but I'm going to take a slightly different tact. Exascale power and cooling will be an issue. But the data movement problem, right now we assume everything, we move the data to the processor instead of the processing to the data. And I think part of the problem we're going to have is there's no way we're going to be able to scale networks up the way we've done in the last 10 years to meet the exascale challenges the way current applications are designed. And I think what we need to rethink the whole model of how we're doing things in terms of how data flows versus how code flows, and it's a complete rethink of both applications and the software stack, as Addison discussed.
Thanks. Gary.
In the interest of being crisp, power, resilience, and programming models.
Is that it? That's it. That's crisp?
Crisp. Thank you. Go ahead, Garth.
Hard to add anything to this, but I think in a deep technical sense, the memory hierarchy is getting deeper. We'll have more caches on chip. We'll have more bandwidth limitations in memory. We have more layers of non-volatile storage in the solutions. And the programmer's jobs to be able to make that completely transparent is going to lead to bad performance. So programmers are going to be forced to have to think an awful lot more about the memory hierarchy. And the worst case of this is synchronization and the way it affects shared memory. And so I think that if you ignore it, you will be inefficient at scale, and if you try to deal with it, you will have a big programming challenge.
So let me jump in again here, Doug. This is one of these things where there's so many barriers to exascale. Your question was, what's the top? And we can all name different top barriers. They're all critical, and you have to be careful you don't just address one barrier in this. It's the classic problem of saying, if we had some ham, we could all make ham sandwiches if we had some bread, right? Solving one barrier isn't going to get you there. These all need to be addressed.
Thanks for that point, Addison. So let's jump into the I/O aspects, and just in general, the hierarchy of I/O that we have, memory, flash, disk, tape, how does that figure into this? And particularly flash drives, which are relatively recent. Is that going to play out in this exascale scenario?
Do you want to take that one?
Sure. So a few years back, we in DOE were asked to figure out if we could afford to do exascale and figure out what miracles we would need to happen between now and 2020 or whenever we decide to do this, if we decide to do it. And I was assigned the task of figuring out if we could afford to buy an I/O subsystem that would work at that scale. And so we did a lot of spreadsheeting and a lot of talking to technology companies to see what technologies were going to be available in that time frame, how many nanometers this was going to be, and how fast that was going to be, and how many bytes this was going to have in it. And we put together a lot of models to try to figure that out. And the models are primarily economic models, and they indicate that in order for us to do I/O with the trends in disks getting denser but not that much faster, we won't really be able to do I/O to disks directly in that time frame. We'll have to do it to some sort of solid-state device that's near the compute node and then migrate the data to the disk. And I don't think this is any huge surprise to anybody, but we needed to prove to ourselves economically that this was the case, and so that's what we did. And so we've been sort of off embarking on pushing on this idea of what I call a burst buffer, but there's lots of people that call it tiered storage or whatever, that you burst to and then you drain the data off to disk. So you're buying solid state for bandwidth and IOPS, and you're buying disk for capacity, which is how those are priced. And it's unclear what will happen to tape. There's a lot of arguments to be made there. I won't go there.
I think that in 2007, I got up and used some failure data to say that we could end up not utilizing very many of the cycles of really big machines if we continue as we were going. And because of the dependence on the I/O subsystem to cover for fault tolerance and the increasing rate of fault tolerance. And the trick there was that the only way to make that work is to make the snapshot capture times, the checkpoint capture times, much smaller. And to do that, you would need a phenomenal amount of disks, and you would have to spend a much larger fraction of your income on the disk, plus all the failure issues with respect of all those disks. The burst buffer, the flash buffer, takes a more traditional approach, and it turns out to be affordable. So I think it's something of a savior to avoid even worse problems in the memory hierarchy.
I'd like to maybe
Sure.
change the discussion. Use the term flash, and I wouldn't use the term flash as we go forward. It might be, and I think Gary used the term correctly, solid-state storage, because the flash, as we know it, might not be the right answer for our problem domain. And the other issue I believe that we're going to face, and Garth and Gary both mentioned it, is we're building commodity, using commodity technology and building upon it to go to exascale. And that is not designed for the size systems we have. And the error rates in the technology are not changing because the consumer and your home users won't pay for this. And as we scale up, we're going to have to look at different resiliency techniques that have not been developed yet to address using commodity technology at this scale.
One important thing in the industry that's already started is at least we've started to get out of the notion that storage is a synonym for disk. It's not. Storage is a lot of different things. And because I'm in the minority, I'll go ahead and say that I think there's an enduring role for tape. If you look, SpectraLogic just introduced its first exabyte class tape libraries, and with things like LTFS are important technology enhancements in the tape realm. I think that'll be an enduring role for certain areas. Obviously disk is there, obviously the solid state drive. So I think as long as we're looking at storage as a concept as opposed to a particular technology, we're going to have the flexibility to say what's the appropriate technology for a particular application.
And you might not be in the minority because I'm on the tape side, as Garth and Gary know, and I actually agree with that. We're going to have some kind of technology that has higher reliability than disk and better bit error rates than flash or disk to have long-term storage or do other kinds of techniques, such as erasure codes or something, on a low power media type. Now, whether you call it tape or something else, we're going to have something that we can, for a lot of customers, that we can store long-term data.
Well, and that's probably magnetic. The mechanism of storage is going to be magnetic, yes.
But the economic models that we did show that even the tape roadmap is not dense enough for us. That's why I said I won't go there, because it's a really long story that I cannot be crisp on.
Thank you. So that begs another question that I think is, to me, very fascinating, and it's simple, is at this scale, how do you know you're getting the right answer? And I'll open that up to the panel, because I think that's a very interesting question.
Check. We're going to check. I mean, that's we're going to get the way we know we're going to get the right answer is we're going to do a lot more checking. Integrity is going to be based on stronger codes. We're not going to get them in the devices if the devices are made for the consumer marketplace where they don't get combined into very large scales. So we're going to add codes at different levels and check them ourselves.
You know, the answer is it depends. HPC has been deployed in a lot of areas where you do eventual, if not previous, coordination of physical to digital simulations. Eventually you build the car, and eventually it gets into a crash, and you see how well that car conformed to your crash models. Eventually you synthesize the drug, and you find out how many people got cured of their disease or their symptoms with however many side effects. So you have some sort of way to start to facilitate the testing of the accuracy of a model. And things like 100-year climate predictions, the check in that case is you stand at the window with a clipboard for 100 years. And you know, you don't really know, are you going to be right? You're trying to do the best you can. The point is that these exascale systems are going to be used for simulations that are not practical to do a physical test on, whether you're mapping the human brain or doing a 100-year weather forecast or trying to do avoid clinical trials of whether a particular drug will affect an unborn fetus, right? It's hard to get pregnant women to sign up for that trial, and you try to simulate these things as best you can.
But Addison, you're kind of munging two issues. One issue is whether the model is accurate and whether the model is predicting something. And I think the other issue is whether you can get the same answers twice. And on your climate model, there's one day you run it, you get this answer, and you know Florida's underwater in 30 years, or is Florida become not a different landmass in 20 years. So I think one of the things that's lacking in discussion, and I know Gary will comment on this, is the standards that are necessary through the standards process to get the change we need so that everybody's on the same page moving forward from the vendor community and are just not happening. And I know Gary and Lee and some other people in a group try to get some minimal standards change in some of the IO stack a few years ago, and it was a failure.
We're already in a scenario today where you run the same floating point calculation on two different platforms and get two different answers. The saying is the only way to test the accuracy of a clock is with a more accurate clock. You could say the same about computers, except in this case you have to have the discussion about which of those answers is right to begin with.
So this decomposes into whether or not the underlying problem is divergent or convergent. And so we worry about the butterfly effect, and perhaps they're divergent. But there are technologies coming up if what you're referring to is non-determinism in the execution. There's technologies being experimented where we make the code run in the same way every time it runs. So you get the same answer, much as a policy of making elections resolve exactly one way, whether it's the right one or not. We're going to make it resolve one way. And so we're developing technologies along those lines to deal with the non-determinism. That's not Panasas. That's actually research way out there. It's called deterministic multithreading.
Yeah, even if it were Panasas, I'd accept it. That's
okay.
Fine.
Okay.
So, and similar along those lines is, so a certain chunk of the performance that we can pull out of a machine will probably be going to reliability and correctness, is that something that we can expect with bigger machines that will be required?
Well, you can, a huge portion of our machines are used for reliability and correctness today. In fact, when we run something, we can't test. If you know what Los Alamos does, you'll understand why we can't test. And
Please don't.
right. And so we don't actually get to find out if we got the right answer that way. Many of our calculations are parameter sweeps to do statistics to try to figure out whether we believe our answer or not. In fact, I would say 2/3 of the cycles spent in the weapons complex are about that. They're running things and trying to narrow the error bars down to where the physicists actually believe the answers that they're getting. And so if you think that these things are always out there doing science to try to get one answer, I think you really don't understand what simulation is about. Simulation is really largely about exploring the problem space and the parameters in that problem space to try to help somebody understand something, to be able to trust it, to be able to make a decision on it. And so I would argue that even today, most of the cycles out there, at least in science, are being spent doing verification of what that calculation is doing and not necessarily doing the calculation itself.
Repeated ones with different parameter settings.
Yep.
Or with new systems with the same parameter set. You look in the weather industry or in the climate industry, if they get a new machine, they'll run through all their old models to ensure and check the data and make sure that they are getting the same answers they got on the other machine.
You also, I think, don't understand the time scale involved in certifying a code that we actually make decisions on for nuclear weapons, right? It's like 9 years to be able to certify that a code really is trustworthy, to be able to make decisions about the arsenal on it, right? So now other sciences that don't have to make quite so, death-defying decisions maybe don't have those kind of cycles, but I think if people think that we run one code and we get an answer and we write down the answer for the director and he goes to the Congress and says it's cool, that's really not the way it works.
I think your original question was about reliability, right? And I'll back up to that. Of course we need reliability in the components, but again, this is an area where the industry is starting to change its view of what constitutes reliability. The traditional way of thinking, if 2% of my nodes drop out, I take a 2% hit to my reliability number for some amount of time, is not the way the majority of the market is currently viewing reliability as a result. Outside the Department of Defense, of course, still looks at it that way. But most people put in a cluster, and if 5% of my nodes drop out, I have an available system. 95% of it is still there, and the system is available. The way that translates going forward is, I think if you're going to have exascale applications, you're going to want them to be able to gracefully handle the possibility that nodes or individual components might drop out. The 100% of the system might not always be 100% available, but the application needs to persist regardless.
I think that's correct. I think that it's less about the fraction of resources we're spending, although that's important, and about the fact that we're going to be dealing with error more or less all the time. So instead of designing for the common case of no error and then having in your pocket a technique of dealing with error when it happens, we're going to have multiple components in the system that are inexperienced, that are being diagnosed to be failed and are being coped with to be failed at all times. And so we're going to change what the normal path is, and that's going to cause a redesign of at least system software, if not application software as well.
And we're going to do this in like 6 or 7 years.
That's the really big problem with all of this, is that 6 or 7 years, you were talking about solid state not being just flash. Well, in 6 or 7 years, getting a commodity, reliable, spin torque tunneling MRAM is just not going to happen. So we phase change perhaps, but
but it's still not necessarily flash.
Yeah, well, economically, I think only flash is going to meet Gary's plan in the 6 or 7 years. But
we will not accomplish all of this in 6 or 7 years. In 2018, we will have systems that are capable of running LinPack at exascale. We're a long way away from having a lot of applications that are going to run efficiently at exascale. That's going to take more than 7 years.
And Gary's applications take 9. before they're, after they're written.
To certify them.
Right. So you figure it's 2018, you're talking 2027. Addison will still be working.
Current
I won't
average,
be.
36 cores currently.
So along those lines, are we going to have to code differently for these kind of machines?
How's that? Crisp? Yes.
Yes. And, okay, then how are we?
So you could redesign code top to bottom everywhere because you have a reason for it everywhere, but you won't have running code in 6 to
Right.
7 years. So
Yeah, and most application domains take, as long as Gary's to get a new code out.
So what we're going to have to do is we're going to have to be very targeted in where we try to make changes and how they can, in small areas, protect against other changes. And that's a hard thing. So some codes can scale up just by turning up the number of nodes, but then what you have is the synchronization problem gets much, much wider, and then the efficiency gets hurt really badly. So there we may end up having to break it up into chunks and try to do something to allow the different chunks to not run in lockstep. And that may be able to be done in a library, for example, instead of in the application core.
But you asked the wrong question, I think. And we made a transition from Fortran to C. Are we going to, the question I would have asked is, a lot of it is, there's still places, that's true, Gary, but there's still lots of old Fortran out there. But
There's a lot.
most of the new development, people are doing it in C, at least in the markets I'm seeing.
Fortran, C, C++, three-way tie at the top.
So are we going to make another code transition to get to Exascale?
Yeah, and is it Java?
No, let's hope not.
Well, that's the ones that are trained programmers.
This isn't the first time this question's been brought up, though. I mean, the HPCS program out of out of DARPA was supposed, this was supposed to be part of all that. We've been through all 3 phases of HPCS. Cray and IBM took it all the way through phase 3. Cray did come to market with their product, and IBM's initial deployment was going to be Blue Waters. Now I'm sure they've still used a lot of those technologies, but the hardware wasn't supposed to be the main point of that program. There were supposed to be entirely new software models that went along with that program, all new resiliency. I haven't seen a wide-scale shift in that. I don't know if it's important to look at, have we had this conversation already? It's just not an easy problem to solve.
If the hardware wasn't supposed to be part of the big part of that, then why did all the money go to the hardware?
You're Mike, do you know that?
I know. I'm old and near retirement.
And Addison, Cray's machine isn't released yet.
Okay.
The Blue Water machine is not the HPCS machine.
No, the HPCS architecture went into I always get the Cray models confused. I apologize. The XE6 has a lot of their HPCS work.
XK will have their HPCS work.
I think we're digressing. The point was the software hasn't come all the way as far forward.
But Gary's right, the money wasn't put into software, it was put into hardware.
And that's always been true, and frankly, it'll always be.
I wasn't intending to fault IBM and Cray. I was just saying that DoD had a program for this where we've put hundreds of millions of dollars. Ostensibly, if you go back and read the mission statement for that, it was to design new models for achieving petascale. Now, we got to petascale, but we haven't effectively changed the software model. We're having the same conversation again for Exascale.
But there are 2 languages that came out of that are somewhat usable, and they're getting better and better, Chapel and X10.
Right.
And when's the last time you wrote a program in one? I mean, none of us have.
And Garth is
I
right.
don't program in any of them, so I'll bow out of that.
And Garth
But
is-
are we standing up here saying Chapel is going to be the answer for Exascale?
Well, it's looking more like CUDA is going to be the answer if you look at the number of lines of code being produced for HPC systems in the last 3 years. Just to be honest about it. Your statement about Java is right. You got to go where the programmers are. You got to hire people because this takes decades. And they're not learning C and they're not learning Fortran. They're learning Java and CUDA.
But there is MPI in our undergraduate parallel programming course at CMU. There isn't yet Chapel. There is a course that has problems that I think are dealt in Chapel. X10 I think they prefer, but But so there's a little bit of it, but the students are mainly learning Java and Ruby and Python. And then you've got the push to functional languages as well, which are perceived to have the advantage that they generate the same answer when repeated. So one solution to fault tolerance is run the code again, but that's not yet been demonstrated as a very good solution for distributed simulation.
So, and thank you, because this is one of those discussions that obviously could go on for the rest of the day.
Thank you for stopping, you mean, Doug?
So let's jump a little bit over to the market, and so when Exascale becomes useful, is it going to be, as obviously a lot of the fastest systems are, a very niche-oriented, only working on a handful of top applications, or is this going to find other places in a market, in this market?
So DOE identified 5 to 7 major app areas to go after Exascale in the 2020 timeframe for apps, and those centers are already spun up, and they're working, doing co-design with hardware people and software people to try to build new codes starting now to run on these machines in 2020. But we picked a very, very small subset of very, very important science apps for DOE Office of Science and for DOE and NSA. So I think in the short term, it's a very, very small number of apps. And then, 20 or 25 years from now, you'll be able to get it on your watch. So everybody will be programming.
And Gary, how much money are you spending for that small number of apps to get it up and running? Or can you say?
A 200th of the amount we're going to spend on hardware.
Okay.
Again.
Yeah.
And again. And
What's
again.
wrong with that model?
The same thing that's always been wrong with it.
Yep.
And frankly, I mean, I don't want to get on my Jack Dongara thing here, but it's that top 500 thing that drives us that way, right? And if we didn't have that, and if we didn't have that in our minds, maybe we would spend more on software. But so there's good to it and there's bad to it, right?
We're at the 25th anniversary now. The original lists that were the immediate predecessors to the top 500 wasn't called top 500 right away. But to your point about the watch, eventually these things trickle down, right? If you took this iPhone and warped it back in time, it'd be on those. I think I have a text on my supercomputer, but. Eventually it trickles down, but it's slow. We are not largely using efficient terascale today as we have petascale systems. And I imagine that in 8 years, when we've got exascale systems out there, we're not going to have efficient petascale applications. We might have efficient terascale applications by then. I imagine we will. We're probably those 2 prefixes behind in terms of what's commonly used, but it does get there.
The number of small companies, small engineering shops that are talking to us, reasonably small configurations, using the same technology, perhaps technology that was developed 10 years ago in the labs, in many cases it was, or 15 years ago, is increasing. So we're pulling a big market behind us. So I think Exascale is going to take a long time to actually be used by a very large market. But the code produced by Exascale will eventually get used, as the code produced for petascale will be used first because it's not there, and the code for terascale is being used now.
Now, I don't mean to get down on these applications, though. The couple of applications we're going to run at Exascale are going to be phenomenal. I mean, these are world-changing pieces of research that you get to do on this. Even if it's only on a couple of applications at first, you can do some pretty mind-blowing things. I look at the applications that start getting run on these petascale systems. It's pretty cool. And the world gets to be a better place with this stuff.
So we mentioned, maybe we shouldn't have the top 500. I wonder, is there some view of who's going to be in the race to get to hit this number?
Let's all vote that we don't care. That works for me.
Or all of the above.
It's interesting, if you go talk to China, they'll tell you that they don't grok why we care about Exascale. They don't understand. In fact, it was interesting. They don't even care that their machines aren't horribly utilized. They said it's a hammer, and when you need a hammer, you go to your toolbox and get your hammer out, and you hammer the nail, right? And then you put the hammer back in the toolbox. And we don't think that way here at all. In fact, I get chastised if my machines aren't 98% utilized all the time. It's really weird. So this is really an interesting phenomenon that we've put on ourselves. And I don't know, maybe it's time to break it.
But it's always been the case. I mean, since, I've been around in the 80s, all the government agencies, you can't upgrade because you're only 90% utilized. And it's always been the case.
Yeah.
And, how do you change that mindset?
You need to have a measurable core set of applications that are paying their way. And where you have them, there's the possibility that you can have a benchmark and a effectiveness. This is worth the money. When we go out and look at what's happening in Google and the internet, they're using very inefficient codes. And they're saying more machines run inefficiently gets the problem done quickly. And so if you can measure that, you can go there. You need something you can measure. And when the codes are too secret to be measured widely and available, then you have to have proxies. And proxies lead to benchmarks. And benchmarks lead to top500.org.
Right, we've been trying to figure out how to measure weapons science for the dollar for 30 years, and it's not easy to measure weapons science for the dollar. It's tough.
But web searches for the dollar.
Yeah, right. How many ads did I sell today is certainly measurable. But we should sell ads. We can produce them quickly.
Okay, so we got a few questions coming from the audience, and one of them is, which takes us off the path we're on and is a little more practical, I think, for many people, is what are your thoughts on the PNFS standard and how it relates to large-scale HPC systems? Any thoughts on that from the panel?
I'll dive in on that one. We've been advocates of PNFS for a while now. The problem is it's late, and the discussion around PNFS hasn't changed a whole lot in the last couple of years. Clients have started to become available now, and I guess that's a step forward, but if everyone has a PNFS client, no one has a server, it's sort of like everyone having a TV but no cable or signal or anyone broadcasting anything. So, we've at least moved forward to where we might see PNFS servers coming out in the next year. The reason we've been bullish on it is because it's got NFS right in the name. And NFS is this ubiquitous standard that people have. And if you can move from NFS to PNFS as you step up, it ought to be a logical progression for people as they grow into high-performance computing, especially in enterprises.
So having been involved in this one since the beginning, I need to defend PNFS's project or progress. The idea may have started in 2003. It got into the charter of NFS in 2004. The long pull was to get the IETF to agree on a protocol, and that was finished in 2008. It then took a year for the IETF editors to turn it into an RFC, which happened January of 2010. And code started getting accepted into Linux in 2.6.37 roughly, with the first real release that you could use, 2.6.39. So 16 to 18 months, and then every 3 months since then we've rolled out another protocol.
I didn't mean to make you defend it. These things happen with multi-vendor consortia and new standards. InfiniBand was like this. It kind of was significantly delayed in the final stages before it came out, and it's done pretty well since it got there, right?
No, what I want to say is that we've been talking about it for a long time, and perhaps we set expectations in a way we couldn't fulfill them. But it is.
You mean like when Panasas launched it in 2006 at ISC?
Did we do that? Well, it was on the charter then, so it was just a matter of time.
It was 2007. I had the year. It was 2007.
Yeah, it's in Linux. It's in the plans are that Red Hat 6.3 will have the first releases supported for the enterprise. Yeah.
So I think
look, Garth, I'm a fan. I am. I'm a fan. I think it's going to do well. I do.
It absolutely is.
I think you have to put it in its right place, though. It's not really going to be a target for running on these exascale machines. I think we would be happy if our stable of capacity-oriented machines, you know, the 10,000 core and less kind of machines today and the 100,000 core and less machines 5 years from now, could run this, right? That way we wouldn't have to, I mean, it would be nice if those could eventually become turnkey for us and we could spend all our time trying to solve the, you know, the problems at Exascale or Zetascale or Yotascale or whatever it turns out to be after I retire. But frankly, that's not true today. We still have problems with even 10,000 core machines and down. They don't work perfectly out of the box. And so if PNFS could help us get to the point to where that's really more of just plug and play, that'd be great. But I don't think it has a play at the high end for a long time, if ever.
Exascale, any of this gets tough. It's hard to imagine luster at Exascale. It's hard to imagine GPFS at Exascale. It's hard to imagine what a file system at Exascale looks like at this point to me. Maybe you've got it figured out, Garth.
Actually, I think the burst buffer technique takes the bandwidth pressure down by a factor of 10, and I think it's much more achievable in the evolutionary approaches because we've got bandwidth. We know how to spripe widely. So we have to deal with the failure cases.
But it doesn't address metadata.
It does not address metadata, and there are other techniques that need to be developed for metadata.
And yes. That, to me, is you know, burst buffer will address the bandwidth issue, but what are we going to do to address the metadata issue? And metadata as we know it is not going to work at Exascale, I don't think.
I'm actually encouraged. There's some interesting projects going on in metadata land right now that look like they have incredible promise.
But you're doing one. So
well, you are too.
Yeah. And we're referring to the notion of middleware. The classic solution that the Terascale and Petascale people did was to take as much as you possibly could of the distributed workload and move it up to the middleware and leave like the OS nodes relatively unchanged. And so there are solutions like Gary's parallel log structured file system that deal with metadata at the middleware level. And then it is something that can change more quickly. It's less prone to the overall reliability, affecting the overall reliability of the system, and can be adopted by individual applications. So that's a nice place to work.
Okay, thank you. So here's an interesting question that came in. What will a compute node look like in an Exascale system? Is it going to be the same as it is today, or are we going to see a different design, GPU, interconnect memory? What do you guys think?
Pretty likely to say there'll be at least some that use GPUs.
Well, the DOE has these swim lanes. I assume everybody's seen the DOE swim lanes in the fantasy chart that we made up 2 years ago. And one says order of 1,000 way parallelism in a node, and one says order of 10,000 way parallelism in a node. And those came from vendors that we talked to 2 years ago and what they thought they would be able to do around 2020. How they do that, whether it's GPU or whether it's, you know, son of Mike or whatever, it doesn't really much matter. What matters to us, I think, is how deep the memory hierarchies are and how much parallelism you have to exploit at the node. And why does that matter? Well, it matters on programming models, and it also matters on how much interconnect bandwidth you've got to have between nodes and how many parallel striped InfiniBand-like things or Cray-like things we're going to have between these giant nodes. So I don't think we actually in DOE are looking at it in the 2020 time frame as will it be GPUs or will it be mics or will it be whatever. We just kind of look at it as how many memory hierarchies are there and how deep will they be and what will the various latencies be and what's the order of parallelism per node versus the whole system.
The processor architecture discussion, I think, is the hottest topic of supercomputing so far. There are a lot of new processors that have come out. I mean, Knight's Corner yesterday coming out from Intel, and the AMD Interlagos are probably the two most notable, but NVIDIA is in there swinging away with new generations of GPUs. AMD has Fusion. Texas Instruments is jumping in with both feet with their floating point DSP processors. They're all over the place. We've got people talking about ARM. The new Blue Gene Q is out with power architectures, and that's not even, it's still ignoring the fact that the K system at #1 is using Sparks. So the processor war is kind of wide open right now. GPUs have the most momentum. About 2/3 of HPC installations are at least experimenting with accelerators, and 90% of those are doing it with NVIDIA GPUs right now. However, in the long term, it's hard to bet against Intel, and the promise of Mike as being x86 base and using Intel tools is very attractive to a lot of users. But watch this space, not just 2020, 2012, 2013 are going to be very interesting years in the microprocessor war.
But there's one thing I'd add to the question is the communications model, in 2016, we're only going to double PCI Express 3 performance. And that's going to be there's going to have to be a significant change there. Because to be able to, process data and communicate at exascale or even at high levels of petascale with PCI Express as a bottleneck, and only doubling every 4 to 6 years is not going to be tractable.
So let's all vote. Can we shoot PCIe in the head?
That's the only thing we got, Gary, right now.
No, actually, you could come off the memory interconnect for interconnects, right? So you don't have to do that. We just choose to because I don't know why we
Dragging
choose to.
along a lot of products that are.
We're dragging along a lot of products.
Correct.
But definitely, that's a weak point. It's a huge weak point, and it has been ever since it came out.
So one of the, I'm going to kind of combine some things, but one of the questions that came in kind of hinted towards power and how much energy it's going to take to run one of these things, and technologies such as optical interconnects and other things that can address some of those issues that might come up at this scale. Do you have any thoughts on that issue?
It's gonna take 20 megawatts to run a machine because DOE wrote it down on a chart 3 years ago.
I believe Google's going to do 100 megawatts. So.
I don't know. I think vendors, when we said 20 megawatts 2 years ago, they looked at us really funny, and now they're telling us 30. So I'm really encouraged. I mean, because I thought it was going to be 300, and I didn't know how I was going to do that. I think I know how I can do 30. I don't know how I could do 300 in one side. So it's definitely a big concern, but it's amazing when people start waving $200 million bills out in front of people what they'll do, and they've really risen to the occasion. They're thinking hard about how to get the power down.
Power is absolutely. I'm not going to improve on those answers, but while we're on facilities, I will say that that my colleague Chris Willard said that we've been through a couple phases now where first everyone was talking about hitting the memory wall. That was a big discussion from a few years ago. Then we started talking about hitting the power wall. We're still kind of talking about that a little bit. Now a lot of the discussion though across the industry has shifted to we're hitting the wall. As in, that wall there, we're hitting it, right? We're up against the edge of our data center space. And this is a problem that a lot of high-end HPC or just enterprise data centers are trying to cope with, is the wall.
Yesterday, there was a paper presented by Sandia, I believe, talking about the power use in the storage subsystem. It was something like 4%, is that right, Lee? So the power issue on the storage side is not as compelling as on and there's choices. If you want to pay more per bit, the solid state technologies will consume a lot less power. So at least in the storage world, I'm not as concerned about power.
Okay. Oh, go ahead.
And floor loading is even starting to become an issue.
Weight,
yeah. Most of our machine rooms are like 300 pounds a square foot or something like that, and these racks are now 2,500 pounds or something, and a lot of people
getting heavier.
And getting heavier, right, because of the water and the densities and all that sort of stuff. So there is some concern that older facilities may have a hard time even holding the stuff up on their raised floors.
You're going to install your supercomputer in the 6th floor and it's going to get relocated to the basement?
But there's still a real tendency to build the HPC data center where the facilities are. And so if you look at the commercial data centers, they're in some sense being built wherever the power and space is most convenient, building new data centers. So we could change, and the physical space and the power availability could track where we can get it as opposed to where we are.
We'd have to move the guns and guards and gates.
And the fiber cables,
And
which isn't cheap.
Which isn't
That's right.
I heard that. That brings a whole new meaning to guns and guards and gates. Finally, a use for the Navy besides weapons.
So I think at this point, because our time is running out, I'm going to give each of the panelists a little chance to summarize, based on the conversation today, what takeaway they would like to give the audience. And then after that, we'll move into our drawing. So why don't we start down the end again with Addison.
Well, it's a big topic to summarize, but
Well, you know,
a couple of main points. It's complicated. I think that we have ingenuity, though, and we will get there. And the first exascale systems will have challenges, and then there will be new exascale systems. And we will figure out how to use them and what they're good for. And the nature of HPC and supercomputing is that this industry is the vanguard of technological advancement. This is really cool stuff. And eventually it gets used by more people with some really awesome applications. I get just as excited talking to people who are doing new engineering things on 8-node clusters. And you know, if it's something new that only they're doing. We push this technology, and it's a worthwhile discussion. These are the right discussions to have, and I'm delighted to be up here with such knowledgeable panelists who are actually the ones doing the work while I just write spreadsheets about it. It's kind of fun.
Well, you know, to be brief and crisp, I mean, this is going to be really hard to do in this such a short period of time with the financial challenges that we have both within the government and within the nation and around the world. And I have serious doubts we'll get there for the types of applications that are going to be needed to address some of the national challenges in the time period that we're talking about in 2018 range. We might get close, and we got to try. It's got to be sort of like the you know, the John Kennedy space program, but we've got to address the problems in a different way than we went from terascale to petascale, because the challenges are greater. They're going up, not the same orders of magnitude, significantly greater orders of magnitude for some of these problems.
Yeah, I would agree. I think, you know, back during the ASCII days, we did 100 teraflops, you know, from 1996 to 2002 or whatever it was. And then petascale came pretty quickly after that, and this is going to be a lot harder, and it's not just going to be, I mean, everybody's going to have to pitch in. It's not just NNSA, and it's not just Office of Science. We're going to have to work together, and it's not just DOE. It's going to have to be other agencies, and I think everybody in the room needs to figure out what they can do to help the nation move forward in this area. And I think everybody out there probably can do something. Smaller sites could release failure data so that I'm not the only one doing that. That would help people, right? And maybe it's easier for you to do that because you don't have to go through 6 layers of security to get 5 bytes out, okay? There's things all of you can do to help this community. And I think everybody needs to put their community hat on and help the nation get here, because that's what it's going to take.
So I want to cast a balance here. Well, on one hand, there's a lot of complexity and challenge, and I don't disagree that significant intellectual and financial resources are going to go into getting systems, and particularly storage systems, up to the scale of exascale. On the other hand, I have extreme confidence that we can do it. I think that the burst buffer lowers the challenge. I think that the wide parallelism is there. I think that we've been dealing with the kinds of scale in control for a while. We can manage that. So I think there's a high degree of confidence that keep the eyes on the prize, we can get there, in the storage world at least.
Okay, thank you. And Gary, I'm struck by your community comment, because I really believe a lot of the HPC market and the growth of clusters came about from a community effort of people working together for a common goal. And I think that's something that, for me, that's the biggest takeaway, that we can help each other in this race. It's just not the supercomputing elite who are on the stage, that it's something we all can rally towards.
That's true. So there's this thing that Garth and I have been working on for a number of years, right? So just an example of this, we install lots of computers every year, right? There's always trucks coming and there's always trucks leaving with, chipper, shredder, old parts of computers. And we said, gosh, could we figure out how to reuse these things? So we take all the non-volatile media out of them and we put them over in a center that we got some money from National Science Foundation to run, to provide large-scale 1,000-size node clusters for systems researchers to use to go have their way with them, right? They can put their own OS on them. They can go cut a wire while it's running and see what happens. There's lots of spare nodes, because there's spare nodes up the wazoo, and they can go put a box over one and heat it up and make it go, crazy and see what happens to the software. So it's called Probe. It's an interesting facility, but it's another example where, if you want to donate nodes to that facility, if some site out there's got a 1,000-node cluster that they're about to deinstall that still has a little bit of life in it, even stuff like that can help. So don't think that you can't help. You probably can.
Because it's a deep pipeline, right? So we unfortunately do our big pushes in decade eras. The trouble is that for the programmer that's going to solve the hardest problem in Exascale, there's a pretty good chance that we're not starting to train that person now. We started to train that person 10 or 20 years ago. So there's a deep pipeline in developing the skill set for the people that can solve the hardest problems. And so in some sense, things like Probe, of making 1,000 nodes available for students to understand what scale is by getting their hands dirty, is investing in the post-Exascale era.
I love the community comments. We're big supporters of the HPC community and like to see it gather together. And if you're in the HPC community and disagree with all of this focus on Exascale and its trickle-down voodoo floponomics, then we can organize a rally, occupy top 500. Come in with your mid-range systems and demand equal funding.
For the other 99%?
We'll have to calculate how many.
Okay, so thank you, and let's thank our panel again. This has been